Hello everyone. So if you remember this general summary of the compounds that we started with at the beginning of the term, now we have reached a point in which we are looking at the last compounds. However, we won't be able to finish, but we are going to cover last bit of this part of the topic. So we are going to talk about a little bit about acids. So mainly, we have a definition that is acids are substances that releases the substance that releases hydrogen when added to water. So that's the key element in every single acid, hydrogen. Hydrogen is always found in inorganic acids. And there are two types of acids, hydroacids, which we briefly covered when working on the game, and oxoacids, which are the new compounds that we are going to look at today. So the key information for hydroacids, they are binary compounds, meaning only two elements are in their formulas. So hydrogen plus something else. More specifically, a non-metal. And more specifically, there are only 7 possibilities for them. So it's only chlorine, bromine, iodine, sulfur, selenium, or tellurium. It's only 7 possibilities. And then the general formula is hydrogen first, always, and then the non-metal. And here we have some examples. Hydrogen with chlorine, hydrogen with bromine, and hydrogen with sulfur. Okay, so this is the key information. And for now, what we are going to do is just to be able to identify a formula. So if I get a formula like this, I know this is a hydroacid, and propose formula as well. And then the second type of acids is oxoacids. What's the difference? These are ternary compounds, so 3 elements are going to be included. And as you can notice from the name, they are called oxo, and the reason is they include oxygen. Okay, so 3 elements, in this case, hydrogen first. Again, always in inorganic acids, we are going to have hydrogen as the first element. That is actually a way of identifying an acid. If I am given a bunch of formulas and I need to identify what are the acids, then I can look for the first element being hydrogen, and that's definitely going to be an acid in inorganic chemistry. So in this case, we are going to have a hydrogen plus a non-metal again plus oxygen. Oxygen is always going to be the last element, as it is explaining here, or also summarizing the general formula. Hydrogen plus a non-metal plus oxygen lastly. And we have some exceptions in this case for these oxoacids, and it is possible to have a transition metal to form acids. There are only a few exceptions, and these are the only 3 that we are going to look at: chromium and manganese with high oxidation states, in this case 6 and 7. These are the only 3 exceptions that we are going to cover. And here we have some examples. Again, as you notice, hydrogen is at the beginning, is the very first element at the beginning, always, and oxygen is always the last one. And in the middle, we are going to have a non-metal, in this case carbon, nitrogen, and sulfur. An example, carbonic acid, which is the acid that is found in soft drinks. Okay, so that's it. That's the general information about oxoacids. So now what we are going to do is to propose formulas. So proposing formulas is something that we have been doing the whole term with oxides, peroxides, and hydrates. So the only difference is now we are going to do it with acids. You already did it a little bit with the game, proposing formulas for hydroacids. So, but just as a reminder, the way we propose is we write first hydrogen, oxidation state +1. This is always something that you're going to see in acids. This is a constant. Definitely hydrogen is always going to be +1 in acids. Either hydroacids or oxoacids, always +1. The only difference between hydroacids and oxoacids is the non-metal in hydroacids has a negative oxidation state, because we have already hydrogen, which is positive, meaning the other element has to be negative in order to add the numbers and get 0 to our general formula. So that's the difference. We have to work with a negative oxidation state. While in oxoacids, the nonmetal has a positive oxidation state because we are going to work with oxygen. So if you remember we mentioned that oxoacids contain oxygen, and if you remember, the most common oxidation state of oxygen is -2. So in this case, we already have a negative oxidation state. We will need the other two to be positive. Okay, so that's how it works. Positive oxidation state for hydrogen, positive oxidation state for the nonmetal, and then lastly oxygen with a negative oxidation state. And that's it. That's what we need to do. So I'm going to explain an example, and then you will be given the opportunity to practice a little bit by yourself. So, for example, for hydroxides. So, as we mentioned before, this is kind of acid that you already work with, but still, I'm going to quickly explain an example. Let's say I'm going to work with bromine, and also I'm going to give you the example with sulfur. So, if we look at the periodic table, bromine has many oxidation states. 1, 3, 4, 5, 7, but they are all positive. The only negative oxidation state is -1. So remember, for hydroxides, we need negative oxidation state because hydrogen, which is the first element, is always going to be +1. Therefore, my second element has to work with a negative oxidation state. So that's why in this case, I need to look for negative oxidation state. In this case, -1. So there you go, +1, -1, it's balanced, so my formula is done. My formula is just going to be hydrogen, bromine, 1 atom for each. If I look for sulfur, the sulfur has 2 negative oxidation states or 1, depending on the periodic table that you look at. The most common negative oxidation state is -2. So again, I write hydrogen first, then sulfur, and their oxidation states. Hydrogen is always +1. Sulfur in this case is going to be -2, and this is not balanced. I have two for negative numbers and only 1 for the positive, which means I need to increase the positive numbers a little bit. More exactly, with a 2 here, and then my formula is going to be totally balanced. And that's it. Those are the final formulas for my hydroxides. We are not looking at nomenclature, that's all we are going to cover, just proposing formulas, and that's it. Now, let's see how it works with oxoacids. So let's say I'm going to propose the formula of acids for chlorine. I think chlorine is in the next page as well. So I'm going to give you an example. Chlorine has many oxidation states, 1, 3, 5, 6, and 7. I'm going to give you as the example with 3, for example. Okay, so we're different. Okay, so if we write in here the general formula for oxoacids, remember that we are always going to have hydrogen first, then my nonmetal, and then oxygen. Okay, so that's the general formula that I'm going to consider in here in order to propose formula for my acid. So I start with hydrogen, I continue with chlorine, and then oxygen. Now, of course, I have to check oxidation state, so that's going to be my next step. So hydrogen I know is +1, it's always going to be +1, and oxygen is always going to be -2. So that's definitely a good start. Writing down the oxidation state that I know that they don't change. So +1 for hydrogen, -2 for oxygen, and in this case, I am going to propose the acid for +3. So I write +3. Now, this is not balanced. I have +3, +1, that's +4 in the positive side, and only -2 in the negative side. So that means that I have to increase the negative number because I have in here a +4 in total and only a -2. So in this case, because I have an even number, it's going to be easier for me to find a number that multiplied by 2 is equal to 4. So I need to add a 2 here, because that way, see if I can erase. Okay, now we cannot. So, because in this case I have, in the negative side, I have -4. 2 times -2 is -4. And on the other side, I already have +1 for hydrogen, +3 for chlorine, meaning if I add them up together, it's going to be a +4 as well. So +4 and -4, that equals 0, and my formula will be complete. So my final formula, remember that final formulas don't include oxidation states, that's only the process. My final formula is going to be this one: hydrogen, chlorine, and oxygen with a subscript of 2. That's what we need to do. Okay, so that's it about this part. I'm going to explain one more example for oxoacids. Let's say, for example, manganese, which is one of the metal with exceptions, with 7. Now, actually with 6, so we get a odd number. So again, I follow the general formula, which is hydrogen, my non-metal, and finally oxygen. Okay, so I need to write hydrogen, my non-metal, which in this case is manganese, and then oxygen. Oxidation states, I know hydrogen is +1. Oops. Oxygen doesn't change either, so it's always going to be -2. So this is +1. This is -2. And in this particular case, I am asked to propose acid for manganese +6. Okay, so this one is slightly different because in here, if I add the numbers, I have an uneven number, or yes, an uneven number. So I'm not going to find a number that multiplied by 2 is equal to 7, a whole number, I mean, because 2 times 3 is 6 and 2 times 4 is 8. But we are not going to get a whole number multiplied by 2 to give 7. So what I need to do is also to increase the positive numbers, because if I manage to move this number up to the closest even number, in this case number 8, then it's going to be easier, because 2 times 4 is going to be 8. So it's going to be, for me, easier to find a subscript in order to get exactly the same number but with a different sign. So that's what I'm going to do. In this case, what we are going to increase is hydrogen, because in here we have a big number. So if we increase a subscript, if we add a subscript in here, we are going to increase the number way too much. So we are going to add a subscript in here for hydrogen. 2. Once I do that, this is going to be 2 times 1, that's 2, plus the 6 that I have in here, that's going to be equal to 8. So from hydrogen, I have 2 times +1 plus the 6 in here, that's going to be equal to 8. Once I have an even number in here, then I can easily find a number that multiplied by 2 will be equal to the number, in this case 4. So my final formula is going to be hydrogen with a subscript of 2, manganese with no subscript, and oxygen with a subscript of 4. And that's it. That's how we do it. We just need to play with numbers, and that's it. So now it's your turn. Could you please propose formulas for acids in these compounds? Where there are 2 or more oxidation states, you only need to choose 1 oxidation state. So in total, you need to propose 4 acids. For chromium, for manganese, in this case 6, because 7, because I already did 6. So manganese with 7, chromium with 6. Carbon you can choose 2 or 4, and chlorine you can choose, except the one that I already did, which was, don't remember, 3, I think. Okay, so choose one of